Hey there, I'm Josh, and this is Slowest Page Ever, how we kept breaking the Codecademy course catalog. You can find all the stuff from this presentation on my website at joshuakgoldberg.com. Slide notes, alt text, attributions. The presentation does include a lot of looped animated images. If those are distracting for you, I'd recommend viewing them in parallel, the PowerPoint viewer online, which allows you to pause them. The agenda for the talk is that we're going to first discover what the Codecademy course catalog is. We're going to dive into a bunch of actual performance problems we did ship to that catalog over the last couple of years. We added too much server bloat, too many scripts on the page, too many React components. We DDoSed or dedicated denial of service ourselves, which was a really fun one. At the end, we're going to give you some cultural takeaways so that you can avoid these mistakes on your own. And then we'll give you some resources so you can learn and read at your own pace. Speaking of which, some ground rules, totally fine to do things at your own pace and not to just keep up with me. I'm always available for questions if you have them, Twitter, here, wherever. I also want to note React is just one way of doing things. There's no one best library among all these modern ones, Angular, Vue, React, whatever. There's no one best way. They all have their pros and cons. We should be respectful and welcome one another. For those who are following along at home or want to take things at their own speed, I do have a companion app that I'm going to be referencing quite a lot here. You can git clone, yarn, yarn dev locally to get it running. All the examples in this talk and in that repository are simplified reproductions of the real issues we faced on Codecademy. That's the intro. Now for the real good stuff. What are we talking about? Codecademy.com/catalog. Fairly standard across education websites to have a catalog page that shows all the courses and paths, which for us are collections of courses that are available to learners. It provides filtering on language and subject area. I'll note we have a lot of courses, so there is a lot of data that needs to be shown in the page. For starters, the page has some context behind it. You can tell based off of how the page evolves, kind of how the people behind the page viewed it. Back in 2019, the team didn't have a lot of time, so they didn't really invest too much in changing the page. In 2020, the DiscoNav, Discovery Navigation team, still haven't figured out why their logo mascot was a pink dolphin named Adolfo. They were a big experimental, fun, change things all over team, so they revamped the catalog a bunch. More recently, the team on the catalog, the Reach team, is more into small iterative experiments, so it's evolved a little bit more carefully recently. The real issue that we need to fix for it though a lot is that it's slow. Users hate slow pages so much. All sorts of studies and experiments and measurements have shown that people go away and you lose money if your pages are slow. So we don't like slow pages. But in order to understand whether a page is slow and get this nice individual, you need to be able to measure. Back in the day, we used three really important native browser events to understand how the old times simple web pages would look. DOM content loaded, where DOM or document object model refers to the structure of the page set up from the HTML elements, was the first one. Once the browser finishes setting up the initial page DOM from the initial page HTML, it would fire this event. Later on, once external resources such as images finished loading, it would fire a more general load event. You can see more on this in the resources linked in the slides. These don't really capture the richness of modern browsers though. A modern page like a twitter.com type of deal could still be in a visually loading state. It could have a finished rendering but still loading spinner seconds after these initial events have fired. So we need a more nuanced set of metrics to really understand how the page perf looks. For that, we often turn to a tool called Lighthouse. Lighthouse is an open source tool from Google. It grades page performance on the attributes mentioned here, ranked by the percentages mentioned here, as a part of a large performance score. It ships as part of Chrome, and it can also be separately run as a standalone tool if you want. My personal favorite metric from this slide is largest contentful paint, how long it takes for the largest image or text block to render, which is a quarter of the score. You don't have to memorize all these now. You can read the more detailed articles on each of them on the great website web.dev, linked here. But we will be exploring some of them. Our first problem, the real deal that we're talking about today, is server loads. or as a user might phrase it, why is this page taking so long to respond? To look at server bloat, we first have to understand, at the very high level, how does a React page get rendered? There are three main strategies that most websites use. There are variations on these, there are new things coming out, but for the most part, these pretty much stay the same. The simplest one is client on demand. The server sends some very basic HTML and all the JavaScript for the page. Then the client creates pages on its own using that JavaScript. The richest is server on demand, or SSR, server-side render for each request, where the client requests the page, the server creates the initial page custom for the client, bespoke one would call it, and then the client later on hydrates that HTML with the served JavaScript. My favorite, the fastest one, is server static, where pages are cached ahead of time and served quickly on demand without very much server logic, if any. And then clients still later on hydrate that HTML with the JavaScript. Looking at these in a little more detail, I realize that's a cursory overview. For the very first one, the client on demand, we have very little server interaction actually happening here. The client requests a page and the server just spits back some very basic HTML and JavaScript. The client starts running the JavaScript and eventually is able to create a page. Hooray! Unfortunately, this does take a while for a lot of clients because there might be a lot of JavaScript and there might not be a lot of power on the client machine. Maybe it's a clunky old Android device that's just been laying around, which is what I use. So we oftentimes rely on a technique called server-side rendering, where the server computes the initial DOM layout of the page, the initial HTML elements, and then sends that to the client on the first request, which means the client can render a very quick cursory preview of the HTML, the initial state of it, before it hydrates and generates the full rich interactive version. So at the cost of the server taking longer to run and having additional complexity, we get a faster, oftentimes, initial page load for the client, which makes users happy, yay. We like fast, and we like happy users. But we don't like having complex servers, and we don't like waiting for a server to crunch the data for every request. So my favorite version of these, the static sites aspect, is where the server might have previously already computed what the page may look like if it's not dependent on each user or request. So whenever a client requests a page, the server can quickly spew back whatever cached stuff already existed. So we get the initial DOM layered on the client as soon as possible. Good stuff. Happy users. Now again, I want to reiterate, there's no best way. There's no single unifying perfect. There are always pitfalls and there are always trade-offs you have to consider. For client-side hydration, where you may not want a server, maybe you want to put more on the client. Or maybe you don't want the server to take too long, but you still want custom pages per request. There are always pros and cons, and you always have to consider them when designing a page. Maybe you do want data on the server, but there's a lot of server data to share with the client, and that's like hundreds of kilobytes. And let's take a look at that particular issue now. So first, we're going to look at how to look at an issue. I got a browser open here. I'm going to right-click on the page, click Inspect, and I'm going to open what's called the DevTools. You might have seen these. These are good for debugging. Today, we're going to use them to look at performance. So I'm going to go to the Network tab, and I'm going to reload the page. This Network tab shows me all the requests that get loaded onto the page, viewing all of them rather than a specific type. You can see that first the document or HTML page gets loaded, then a bunch of scripts. I'm also going to note that I like disabling cache because it's hard to verify performance if the browser caches from one experiment to the other. So I'm going to make sure that's checked. Very good. Now, each of these requests comes with a little bit of information, how long it took to wait for the server, the TTFB, or time to first byte from the server, how long it took to download the page from the server. So I'm going to go to an example page, server bloat, which is the first on these issues. And this is one where we've set up the server to A, take too long on the first request, and B, send a whole lot of HTML down with the page. So you can see that this page is pretty huge. It's got a lot of these little card things, each of which represents a course or path on Codecademy. In fact, just to show off how huge this page is, I'm going to right-click View Page Source, copy this into, let's say, VS Code. I already have these open. All right, so we got the page here, and we can see, wowee, that's 613,000 characters. Wow, that's a lot of stuff. That's not good for performance. And if you really want to prove that it's not good for performance, let's go to the page, filter to just documents, so we see this thing, click it to open its subtabs that explain specifics about it, and now look at the timing tab. This timing tab shows it taking almost 100 milliseconds, almost a tenth of a second, just to wait for the server to send the initial data. And then another, let's say, 60 milliseconds or so to download that data for the server. So we have over 165 milliseconds before the page actually loads. Now you might think, that's less than a quarter of a second. That's not so bad, right? Well, a quarter of a second for a page to download its first HTML is kind of a lot. There's a lot of stuff that can happen after this that still needs to happen for the page to become interactive. You still need to load more scripts, maybe some more images. So waiting a quarter second, tenth of a second at the very beginning before you can do anything else is kind of painful for the page. So we don't like that. One technique we can do, we go to server load fixed, is to load only part of the page at first, and then later on asynchronously fetch the rest of it. Ta-da! If we look in the network tab now, for this fixed version where the server does a lot less work to set up the page initially, deferring until later, we see that the timing is a lot more friendly. We have less than 25 milliseconds to wait for the TTFB, time to first byte, and less than a millisecond to download it. So that's a lot better. That's much, much more performance. And if we view source again, and copy and paste into VS Code, you see there are only 32,000 characters in here. Not so shabby after all. Cool. So that's one fix we can do. Don't process data you don't immediately need. If there is dynamic data on the page, stuff that the server has to send down, maybe only send the first few inches visually of it, and then later on load the rest. I really like static pages because there's no server component. They can just immediately spit back what they already cached. But if you need dynamic data, there's a trade-off. Always with the trade-offs. Another problem. The HTML, the DOM of the page can be overloaded. Sometimes the scripts are too. So users might be asking, after the page first, say, renders or starts to load, why does it take so long for it to finish? Now, Codecademy actually is not so bad for this. I'm pretty proud of us for not having 3 versions of jQuery or whatnot. But you would be shocked how many sites have duplicate jQuery or Moment or whatever. All these random, unused, unnecessary scripts that pages load. So let's look at another issue, script bloats, where we've set up a page here that has a whole bunch of unnecessary JavaScript dependencies. All this stuff, 3 versions of jQuery. Who needs 3 versions of jQuery and UI and the slick library and data? All this stuff. That's too much. So we can see under the network tab, stop here, that we load like 2.5 megabytes plus after transfer over the network compression, so after gzip, the fancy compression browsers use. And then when we uncompress it, that's over 9 megabytes of JavaScript resources. That's ridiculous. Who needs that? So I'm going to instead look at the performance tab now to really understand how this impacts what's called waterfall. The waterfall is a friendly term for the description of how all these resource loads start on the page. Let's try again. There we go. So after we initially start loading the page, we see a few JavaScript things, and then we see this long wait where we're downloading script codes here. And then at the very end, after we finish loading all these different scripts, we see the little indications of when those fancy events we were talking about earlier happen. DOM content loaded, first paint, or first contentful paint now. For the largest contentful paints, the browsers actually give us a nice little preview of which element is considered the LCP, which I think is kind of cute. Now, this is not that bad. It's only half a second, but if you fix it, you'd be surprised at how much better it can be. Script bloat fixed, clear, Start profiling and reload page. Wow, that was fast. For this one, it's much faster. Now the waterfall doesn't look too different, but when you think about how we actually finished in, what is this, 300 seconds to load, gets a lot better. But we should know also that the metrics we're looking at here, the fast internet speeds that I'm using aren't really representative of what a lot of users have. Many users have equivalent to fast 3G or even slow 3G. Say they're in a rural area, or their computer is slow, or they're sharing Wi-Fi with a bunch of people. So in the network tab, it's pretty useful to be able to throttle yourself down to, say, fast 3G. And if we go back to the script load page and wait for the network to load, look at that. That is a spinner right there. That's taking a while. Oh boy. All right. I'm going to clear, and let's go back to performance and start profiling and reload the page. That's taking a while. So you should note that even though it might be zippy and fast for you to load a bunch of extra scripts, for your users, it might be a pain in the tush. I'm getting impatient, so I'm going to stop. Oh, there we go. So for a user on fast 3G, unlike us before, where it didn't really seem to make too much of a difference, all these scripts here took 6-7 seconds to load. Their events are at what is this, 15 seconds after you started? Ridiculous amount of time. But if we go to script load fixed, then start profiling and reload the page from Brave. We see that it gets reduced quite significantly to maybe 10 seconds. I'll note that a lot of these measurements are pretty imprecise. You should really respect that network results fluctuate a lot. And if you really want to measure things, try doing it quite a few times in a row per experiment to get averages and remove the outliers from those equations. Say reducing from 15 seconds to 10 seconds now was pretty nice. In my experiments, I sometimes reduced from, let's say, 6 seconds down to 2.5 seconds. So it really depends on what you're doing with a computer, your network latencies. A few takeaways. Similar to HTML, don't do things if you don't need them yet. In this case, don't load scripts you don't need. Mobile/low bandwidth users are particularly hurt by them. Also recommend learn how scripts delay load if possible. There's a reason why script tags go at the end of the document body, so that the DOM can render before them, because the browser knows it has to stop, pause, or rather, as we call it, block rendering while it's executing a JavaScript script, unless that script is marked with async or defer, which are two slightly different attributes that allow the browser to defer rendering that script. Specifically, code splitting is a really nice way to, in your code, say that I don't need something until later. If you're using bundlers such as Webpack, you can use these fancy import statements. Browsers have started natively supporting them as well, where the import statement takes in a path to a file or module and returns a promise for that content. There's a snazzy new feature in JavaScript called ECMAScript modules, ES modules. The way you do it in code, it's a little more complicated than your normal imports. On the left, the before, you might say import Fuse from Fuse.js. I don't remember what that library does, it's not important. On the right, instead, you might write an asynchronous function that awaits the import of Fuse when it's called. So you don't load the Fuse library in your code until you actually need it. So that's a nice little strategy. We're actually going to go a little bit more into code splitting with the component load section here. So let's say that you have a specific React application, what this presentation is all about, and you want to know why that React component is taking so long to render. Similar to before, excess crap on your page, in this case DOM, is an annoying killer. If you have too much DOM on your page, if you have too many React components that are doing too much work, the page takes longer to load and your users hate you. So just right off the bat, try to limit the amount of stuff on your page. Again, whether it's React components or initial DOM or scripts. Wait until complex areas positioned outside the visible viewport really need to be rendered, which is often not on initial page load. Let's look at this component bloat page, again, throttling down to fast 3G. So this page is a specific type of script bloat where it's a lot of React dependencies. I'm going to throttle it down to fast 3G and go to performance and start profiling and reload the page. So this thing is set up so that there's a big component that isn't always visible. It's hidden until the button is clicked, but that big component does a lot of work. It has syntax highlighting and list virtualization and all sorts of random stuff. And we can see that on 3G, it's taking upwards of 25 seconds to load. Wow. I'm impatient. I can't wait now. It's been 30 seconds. Okay, there. So yeah, here's this huge component. It's even taking my browser a long time to render the performance waterfall. And because it all needs to happen up front, this page hasn't been optimized at all. We have this huge JavaScript file, componentbloat.js. Oh boy, the timing on this thing, I'm sure, is horrifying. Let's see, componentbloat.js. Yeah, 28 seconds to download. Ridiculous. But what we can do, if we're clever about our performance, is we can realize that component didn't show until we loaded the button. So instead, we can, just gonna wait again, that profile. We can make the page not load the component until we click the button, at which point then the component loads in eventually. So I'm not even gonna bother waiting for that one, although it is faster. We can see in the screenshots of the performance profile that instead of blocking for a second and taking all sorts of time on fast 3G to download the component, if we React code split using the import, and it takes a lot faster to load. Just while this stuff is running, this is a particularly good way to use the React imports. Just wanted to skip straight to the syntax here. A lot of frameworks like Next allow you to create these dynamic components where they take in a function that async imports a component and then give you back a component you can use that's the equivalent but lazy loaded. In this case, instead of directly importing the hello component, we need dynamic loadings. So now the performance profile is a lot better. We only block, meaning time until the user is able to interact with the page for a little over a quarter second instead of over a second. And it's under 2 seconds to load, which is a lot better. So yay, good for us. One last problem to go over, self-DDoS. It's not always a performance issue, but it's certainly an issue to deal with. A DDoS, or dedicated denial service, is when someone sends so many requests to a server that the server cannot handle the load. And I want to give some context here that, like with any UI state management frameworks, React components can be really tricky. There's a bug in this code. Props to you if you can find it before I switch slides. No worries if you don't. React gives you a ton of control, but inherently code is complex. This is true for both class component lifecycle methods and effect hooks, that it can be really easy to mess it up. Too late if you didn't find it. That's all right. So for self-DDoS, the last issue we're looking at, this page seems to work fine. Looks good to me. But if we go into the dev tools and look at the network tab, we switch to fetches, or exit jars as they're sometimes referred to as a subset of. Oh no. Oh no. Look at that. Look at that little waterfall. Look at all those requests come in. This is unfortunate. Clearly there is a bug in the page that it's sending the same very quick request over and over again. We just reached 200. So if you're a user, you might not notice this, but if you're Codecademy and you have thousands upon thousands of hopefully very happy and lovely users sending this to your server, that is a nightmare, and you do not want that. In this case, if you have an effect that fetches some data that was supposed to be async or lazy loaded, make sure that you only fetch that data when you need, if, say, the user that it's populating doesn't yet exist. This was a one-line fix. So if we look at the fixed version of this, where we Wrong way, so DDoS fixed. We go to the fixed version, we see there's only one request user. I'll go back to the code. I realized that was a little fast. So yeah, here we just don't fetch or don't set the timer for the fetch if there's already a user. We only do it if there isn't. Code. So, rule of thumb, check yourself before you wreck yourself or play yourself. If you substantially change a page, let's say mess with its caching or API, just check your dev tools. Make sure you're not DDoSing yourself. Make sure your API calls are being sent, say, at the right time, to the right URL, the right data is in them. Even if you don't notice page performance suffering, it might be that you have something funky going on in the background behind the scenes. This particular graph is a good representation of what we did. Pardon the typo on it. We had to revert the deploy. I'll admit, it was my deploy. I did the thing. I broke. But users still had the page open, so they were still spamming our services. This graph is of the delay, the response time on average for that one particular service that was getting DDoSed. Spiked that up to almost a second. So we had to deploy a second code change that added some aggressive caching. So yay performance. Fun times. Don't DDoS yourself. Anyway, some helpful strategies to make sure that you don't have this happen to you. To start, keep performance in mind early. If you're creating or updating a page, think, where does the data flow from? Is it going to be difficult to request that data? Is it going to be required for the first page view? Only later on. And make sure to have the conversations early when the page is being designed. Don't wait until the implementation phase. You definitely don't want to talk to someone and say, hey, I'm sorry you spent all this time on these designs. They're beautiful, but they're impossible and we need to completely redo them. That's a miserable time for a designer and for a developer. That being said, architect well, but don't sweat the small stuff too much. Certain Donald Knuth, famous person, once said, premature optimization is the root of all evil. There is a caveat that sometimes that remaining 3% of when it is important to optimize is important. But unless you really know something needs to be optimized, maybe don't. JavaScript engines are pretty fast, so if you're starting to argue over things like for each versus for of versus loop methods, it's probably not important most of the time. I also want to mention, don't assume your users and your performance learnings are both going to surprise you. I came into a lot of performance investigations thinking, oh, we should do it on the server. Oh, we should do it on the client. And then being surprised at which one was better suited for that situation. Users, for their part, were going to completely surprise you. They have all sorts of weird network setups and devices, fast computers on slow networks, slow computers on fast networks. You don't want to be in a situation where, thank heavens, I've never been in this, but I know people who have, where it took like 14 seconds for a particular country to load the homepage because, oops, they forgot to test there. Don't do that. Lastly, if you have any kind of retrospective or post-mortem when something goes wrong, great. If you don't, highly recommend starting it. When something failures, investigate why, don't just fix and forget. Maybe have a meeting to discuss learnings. You definitely don't want to make the failures about people, individuals, because most of the time, A, that's embarrassing. It makes people not want to admit to failures. But B, it's really systems that fail. So I recommend the 5 whys strategy. Keep asking why a problem happens, arbitrarily at least 5 times. This is a legitimate engineering strategy with a Wikipedia page. And you'll get to the root of things. Maybe it's not that a person messed up, but that a system didn't stop them or didn't catch the bug when it should have. Lastly, a few useful resources. For debugging using the dev tools, Google has some great documentation. Highly recommend. You can see these in the slide notes, no need to write them down now. For performance, web.dev is a great website. The MDN docs are pretty good too. React has a dedicated page. Speaking of React, their website has some good stuff on their fundamentals too. And little shout out, Codecademy. We're pretty good at teaching, I think. All right, so just to recap, we talked about the catalog, about several issues and really annoying DDoS that happened with it. We gave you some cultural takeaways and some resources. That's all that I have. Thank you for listening to me. My Twitter and my website are joshuakgoldberg.com. Feel free to reach out. Cheers.